Hi everyone, welcome to my talk, Reducing Inactionable Alerts via Policy Layer. My name is John Seymour, aka Delta Zero, and I'm a lead data scientist at Salesforce, where I work on the detection and response team, performing machine learning on security logs to alert to new attacks, to improve our existing alerts and rules, and to find and make new contextual data for use in investigations. My goal here today is to inspire you to be creative in where you apply data science and machine learning techniques. A major impact can be had with very small amounts of effort. If you come out of here with a nagging feeling that machine learning would help you with somewhere it's not normally applied, then I'd call this talk a success. Right, so like a lot of good presentations, let's start with definitions. Oftentimes, humans analyzing model-generated alerts will throw an alert away immediately, right? And we've found as we've deployed our models, there are two main reasons what we've seen how this happens. First, when there are issues with the data pipeline. So these are things like when necessary logs are missing, when parsers fail, when joins between host and network artifacts behave unexpectedly, when third-party information is bad or corrupted, when deployment inconsistencies throughout the fleet, when added contextual information like host names is wrong, when added contextual information is stale where it used to be right when it's wrong, when added contextual information is right in an unexpectedly way. This list goes on and on and on, right? Contrast this to like obvious false positives, where we mean the model is not able to capture the complexity of the instance, where the activity can easily be determined to be a low priority or a non-existent threat to the business, such as a model alerting on beaconing to a company-owned resource. Generally, we've seen these handled after the fact. A whitelist is added, which says simply, even if the rule or the model says this is bad, don't alert on it. You can think of whitelists as a simplistic example of a policy layer which addresses the two causes for inactionable alerts. In this talk, we'll demonstrate how even simple modeling improves upon whitelists, and further we'll argue how modeling whitelists separately from modeling suspicious events is actually a natural approach to the problem. So here are some reasonable examples for whitelisting we've seen in the past, right? For a large number of alerts generated, we don't actually care about if a connection is completely internal to the network. So for these, it might actually make sense to whitelist anything that where both the source and the destination are internal. Or we might only care about a connection attack that's successful, right? So we might think filtering alerts where the connection was ultimately unsuccessful, like maybe the firewall blocked the connection, we might think that's a good idea. Or another widespread use for whitelists is in filtering if the domain is obviously benign. So like take the top popular domains and just shove that as a whitelist and say don't alert on any of these things, right? And these are obviously common and widespread ideas. But whitelists create some unintended side effects down the road. They're extremely rigid. If a whitelisting rule matches an event, then the event is just completely discarded, even if the activity is extremely suspicious for other reasons. They're also challenging to maintain, right? If you've worked with whitelists, you've probably noticed issues with updating them, since each problem set tends to have different whitelisting requirements. For example, take an extremely loud attacker moving laterally through a network. You can't whitelist internal connections for that. Or take failed connections. They could be NX domains today, but future command and control instances where the malware just hasn't activated yet. Large number of these might also indicate an infected host or something like that. And benign domains. A major way to exfiltrate information is through standard services that are likely whitelisted. Not even considering the fact that domains aren't static and most popular domains, or out of popular domains, not all of them are always benign. So I bet that most of you in the room are thinking, okay, we'll just include those as features in our models. And that's definitely a reasonable position to take. But here are some reasons why you might actually want a separate policy layer, at least at first. Let's start easy. Whitelists are already accepted by human analysts, and stating this alert has whitelistable characteristics, but we think it's suspicious even given those, is actually still generally well received and useful information to the analyst. However, model-centric reasons exist for such a separation too. Google Rules of Machine Learning advocates for separating spam filtering and quality ranking in a policy layer, and that a quality ranking should focus on ranking content that's actually posted in good faith. The main idea behind that rule is that spammers, the adversaries in that context, will attempt to emulate high-quality posts. So features used to indicate high-quality posts today might actually be indicative of spam tomorrow. That concept of adversarial drift also applies here. And the independence of the two types of models actually really helps with tuning training frequency. We all know that adversaries adapt. They're likely to adapt faster than what makes a model an alert inactionable. Also, separation gives us generalized ability, which allows for centralization, reducing code duplication. Most of these features will be present in a large number of rules and models that you use. So even if most models exclude some of these heuristics, you can still have one whitelist model which applies to a large number of rules or models. Another is good data is actually the limiting factor for model quality in the intrusion detection space a lot of the time. Separating actually reduces the problem space so that models don't have to learn both what's a good alert, what's likely to be thrown away, and what's actually suspicious at the same time. And that actually means you can label data for different tasks and be a lot more effective with your labeling. And then finally, some of our team's models have multiple consumers with contradicting preferences. These might actually be unsatisfiable if you try to push them into the detection model. So how do we actually enforce the heuristics commonly used to filter false positives in a better way? Well, here's a simple machine learning-based approach that we've deployed at scale for doing so. We actually combine these heuristics using a function which penalizes alerts where any such issues are found without completely filtering the behavior. Concretely, if we let X be a list of binary heuristics which are commonly used to filter false positives, then let your policy score be some number between 0 and 1 raised to the count of how many of these heuristics are true for a given event. For example, if lambda is 0.5 and you have 2 issues surrounding the data, then your policy score would be 0.25. Or if no issues are detected, your policy score would be 1. And we just reweight the alert by this value. Right, so this is a really, really simple approach, and it's also simple to integrate with the models. Actually integrating this score with rules and models is very straightforward. You just multiply the 2 different scores together. It also has a lot of other benefits, though. The model can be reused for many use cases. So even in instances where the heuristics conflict with the actual model generated, such as that exfil detection model using good domains, you can actually just reweight the final alerting threshold for the combined score. Another benefit is the model is completely unsupervised, requiring 0 effort to train. And the model requires very little data science background to actually understand, right? But perhaps most importantly, it allows you to aggregate all of your different heuristics in one place, which makes it much, much easier to maintain. But we know there's no free lunch when it comes to these sorts of things. So what do we actually lose when we're moving to this sort of model for whitelisting? Well, to start, the main change is that we're now allowing a small number of events through that we wouldn't previously. So there is definitely, by definition, going to be a non-zero number of false positives. We've mitigated this quite a bit through thresholding, but obviously some of the new alerts that you get are going to be true positives and some are going to be false positives. A piece of low-hanging fruit that you might think is that the model is actually very, very simplistic right now, right? You could, for example, train it on historical data, like previous case adjudications. That's definitely something we're looking into. But probably the primary drawback here is how the model handles repeated alerts. With whitelisting, you can completely negate an alert from being generated, but you can't do that here. You can reduce them by adding sort of features based on prior case adjudications, but that makes the model complex. You could also eliminate them by adding additional, hopefully temporary whitelists, but that brings us back to the initial whitelisting problem, and it reduces a lot of the impact of this approach. But here are the main issues that we're trying to improve upon this. First, again, the most obvious being supervised learning, which would allow us to more finely tune that policy layer. After that, we plan to try out different stacking methods. So using like the output of the policy model as a feature when training the suspiciousness model and trying different configurations for that. And then finally, we're trying to more formally incorporate the consumer preferences, like we stated earlier, such as different outputs for threat intel versus our SOC, or for the different responders for risks, vulnerabilities, and policy violations. So that's actually all I had. Does anybody have any questions?
Hi, thank you. Quick question for you. One of the big problems that I've experienced in the past with trying to kind of work with ML systems in general is the problem of introspectability. And for, coming from an ops background and having been the person getting woken up at like 3 in the morning, nothing is worse than having something like sometimes tell you one thing and sometimes tell you another thing, and like you can't figure out what the hell's going on.
Yeah.
How have you dealt with, while working with your customers, like dealing with that kind of problem of not necessarily being able to introspect the system in a easy to understand way?
Yeah, that's definitely a great question. So for the actual whitelisting technique here, it's actually very easy to introspect, right? Because you actually have the values of the different variables. You know how many are set to 1, et cetera. You can just return those to the ops people. Adding in something like a supervised method or something like that, yeah, that would definitely obfuscate, for example, and would harm the introspectability, right? For this, we have issues, for example, with our host name mapping, for example, IP host name mapping. And for those, we actually encode that into our policy layer by saying, okay, this is known to be faulty, IP host name mapper, right? And we can surface those to whoever's investigating the alert.
Hi. So to someone who is completely unaccustomed to ML in general, what strategy would you say is best for determining a proper lambda, and how would you really tune that appropriately?
Okay. So I would probably do it the same way we actually did it, which is start at just lambda equal 0.5. So that means for every extra alert that you generate, then you half basically the score, right? The output score. If you wanted to tune it further, you'd probably need actually to get data and collect data about how many alerts are good and how many are bad coming out of your system. And that's when you want to actually move to something like a supervised approach anyways to sort of tune sort of that lambda. You could also have, say, a different weight for every single feature if you did that technique, whereas here we only have a single lambda for efficiency. Cool.
Sort of related to that, did you, as maybe a middle ground, look at talking to the analysts and seeing what they thought about the different alert types and assigning different weights based on their feedback?
Yeah, so we did definitely talk to the analysts, and we did consider assigning different weights to each, different heuristic that's being true. The only issue with assigning weights here is basically that sort of explodes the dimensionality of the problem, right? Like you have a different weight for every feature, right? Whereas right now we only have one sort of parameter we're tweaking. And so we decided that basically if we did sort of attempt that route, we would wait until we actually had a collection of data that we could use to sort of label things as being, well generated or not, and then just go a supervised approach anyways.
So just to make sure I'm understanding right, each feature is or each element in a whitelist is going to be a feature in the policy layer?
Sort of. So, for example, if we have like a rule that says it's a domain that's in a whitelist, or we have a rule that says, okay, the host name is missing from this particular log, or we're missing the parent log, or things like that. Those are all rules that we would use as separate features in that.
So, do you have any thoughts on how to handle the model expanding as you come up with new heuristics,
Yep.
over time?
Yeah, so that's also comes back to the sort of supervised training approach. If you start something simple like this, like really simple, then you can sort of get a lot of those ideas out and know sort of a lot of the different rules that you have. Even so, I guess you're probably going after the idea that like even if you deploy a model today, then later down the road you're going to discover some new inactionable alert rule or something. Oh, okay. Well, I was going to say, like, we're kind of assuming here that the drift in terms of what makes an alert inactionable changes much, much more slowly than the suspiciousness sort of score. So adversaries adapt, but your system doesn't adapt that fast. Cool.
All right, well, if we have no more questions, let's give another round of applause. Thank you.